This video is to introduce you to the idea of latent heat. Before we get to that definition, let's take a look at this graph depicting the phase changes of water. You notice here, I've got amount of heat being added to a sample of water on the x-axis, and I have a change in temperature on the y-axis. Take a moment, pause this video, and ask yourself what's happening at each lettered section on this graph. What's happening between A to B, B to C, and so on and so forth. You might have noticed in the graph in the previous slide that when a substance is beginning to change phases, the temperature of that substance temporarily stops changing. And that's because all of the heat we are adding into that substance is being transferred into the molecules to break apart those forces that hold them together. The forces that hold those particles together are called intermolecular forces. So here's your first definition to write down. An intermolecular force is a force that holds particles together in a substance. And the more tightly packed those particles are, in this case molecules, the higher the potential energy, the lower the kinetic energy, because there's not a lot of room for those particles to wiggle around. The less tightly packed those particles are, the higher the kinetic energy, the lower the potential energy, because the molecules have a lot of room to move. We're going to take a look at this little simulation here. You notice here, before I hit play, you have a picture depicting some water molecules. And you will see that the oxygens are always represented by red. The hydrogens are always represented by white. And here's a great example right here of a water molecule, because water is H2O, has 2 hydrogens and 1 oxygen. This is water in its solid form, or ice. And I know it is because all of those water molecules are packed rather tightly together into this beautiful lattice form. A lattice form that will later cause the formation of snowflakes, which we can talk about a little bit later on. If I hit play here, I'm going to begin to add heat to this sample of water, and very slowly as I add heat, you'll notice that over time the water molecules will start to gain thermal energy, which will transfer to kinetic energy. And here they go. So here's the water molecules as they begin to heat up. Notice that the potential energy is decreasing, the kinetic energy is increasing the internal energy of the water, and here are the water molecules changing to a gas. And so that's the highest point where they have the most kinetic energy and the least amount of potential energy. Here's another picture that depicts this. So the intermolecular force that holds water molecules together is called hydrogen bonding. It's a field force, and later in your educational careers or next year in IB chemistry, you're going to be learning about why in particular oxygen has a negative charge and hydrogen has a positive charge. However, for the purpose of this lesson, you just need to know that oxygen is negative and hydrogen is positive. When you have water molecules in the presence of each other, the hydrogens from one of the water molecules will be attracted to, magnetically, the oxygen in another water molecule. Positive attracts negative. And the colder the water sample is, the closer that bond becomes. The warmer the sample is, the further away that bond is, and the more likely that sample will be to be a gas. Hydrogen bonding is the strongest type of intermolecular force between two or more nonmetals. There's a bunch of different types of intermolecular forces, but for the purpose of this, you just need to know about hydrogen bonding. So, as mentioned when we looked at the simulation, the potential energy in the intermolecular forces will begin to transfer to kinetic energy as you add heat to those particles. When the particles have increased their overall kinetic energy, the phase change has occurred. And because the heat is going to weaken those intermolecular forces, instead of raising the overall temperature of the substance, the temperature stops changing for a certain period of time. When the temperature stops changing, however, energy is still being added to the substance, we call that heat being added latent heat. And there's the definition of latent heat. Latent heat is defined as the amount of energy per unit mass, usually kilograms, that's added to a substance during a phase change. And the energy being added at that point in time is not raising the temperature of the substance. Here's the formula in order to calculate latent heat. We are still using capital Q as the symbol for heat. The subscript state just means state of matter. So the state here is going to be from solid to liquid or liquid to gas. That's usually written as a subscript by the letter Q. M is mass in kilograms or grams, and capital L is the latent heat. How much heat is added per kilogram per joule. The next thing you're going to see here is a table of latent heat values. Do not write down this table. It's a waste of space. You will always be given the literature values for latent heats. Well, what you'll see here are two different types of latent heats in this table. You'll have latent heats of fusion and latent heats of vaporization. We think of fusion as combining two things together. However, when we're talking about heat transfer, fusion actually means changing a solid into a liquid, which is kind of counterintuitive because you're thinking about pulling those water molecules apart. So heats of fusion have to do with changing from a solid to a liquid. Heat of vaporization is going from liquid to a gas. So there are opposite latent heats here. We can have a latent heat of freezing, which is the opposite of fusion. And we can have a latent heat of condensation, which is the opposite of vaporization. If you look through this list, you'll notice that substances that are gases at room temperature will have the lowest latent heats, whereas substances that are solids at room temperature will have the highest latent heats. And that makes all sorts of sense because it'll take a lot more heat to change copper into a liquid than it will to change water into a liquid from ice. So again, here are these definitions of heat of fusion. Remember, fusion isn't bringing together in this case. Fusion means changing from a liquid to a solid or a solid to a liquid. And if I'm going from a liquid to a solid, my latent heat of freezing would be negative. Latent heat of vaporization is going from a liquid to a gas, or the latent heat of condensation is going gas to a liquid. One important note here is that all of these latent heats are calculated at standard pressure of 1 atmosphere. When you get into gas laws next year in chemistry, we're going to change the pressure around. However, in physics this year, just assume that the pressure is not changing. Here's an example problem, just like the ones on page 319, numbers 1 through 5 you're going to be dealing with. How much less energy is needed to convert 50.0 grams of solid aluminum to a liquid compared to converting 50.0 grams of liquid aluminum to gaseous aluminum? I'm going to use latent heat equation 2 times. First time I'm going to go from a solid to a liquid. And the latent heat for this one is going to be the latent heat of fusion. And the second one I'm going to use is going from a liquid to a gas. And here it's going to be the latent heat of vaporization. So the table I gave you, the masses are in kilograms. So for both of these, I'm going to take the 50.0 grams, convert it to kilograms, and that's the mass I'm going to use in both cases. Latent heat of fusion is going to be the 3.97 times 10 to the 5th joules per kilogram. This mass is also in kilograms. Let's move this one down below. .0500. Latent heat of vaporization for aluminum going from a liquid to a gas is 1.14 times 10 to the 7th joules per kilogram. In both these cases, kilograms going to cancel out. And I can now find how much heat is needed in both these cases to change between these states of matter. 0.05 times parenthesis 3.97 times 10 to the 5th. First case I need with 3 sig figs, 19,900 joules. And in the second case, which I should need a lot more, I need 5.70 times 10 to the 10 to the 5th. Change this to scientific notation for clarity. 1.99 times 10 to the 1, 2, 3, 4th. Then the last thing I need to do is just subtract these two values. So how much more heat is needed? Well, that's going to be 5.70 times 10 to the 5th minus the 1.99 times 10 to the 4th. And what we get is I need 5.50 times 10 to the 5th joules more heat to go from a liquid to a gas. Makes a lot more sense because once a substance is in its liquid form, the particles already have kinetic energy, so it takes a lot more energy to get them to release some of that potential energy that could be stored between the molecules. So hopefully this helps you solve page 319, 1 through 5. See if you can come on Wednesday with the best guesses on those questions. Have a good morning.